Okay, is it full screen?
I see it sort of in a lower left corner, like occupying maybe 2/3 of the screen.
Oh,
Is that what you see, Mayar, as well?
Yeah, now it's okay. Yeah, it was frozen, I guess, for a few seconds, but now.
Let me put it on full screen again. So the PDF will show, so worst comes to worst, one can use that, but full screen would look better. Is it good now?
It's very weird. It just goes into occupying like 2/3 of the screen on the bottom left, but.
Okay, maybe I will stick with, right now you see the PDF, but not on full screen, right?
Yeah. I guess if you have two screens at home, sometimes it's showing the other one. So you need to choose which one you share through Zoom.
Yeah, let me try it again. If not, I'll just use the PDF. I just recently changed my laptop, so maybe that.
The other things I do sometimes is that I put it in full screen first and then I share it.
Ah, that's better. Okay, let me do that. Let me try that. I'll put it on full screen first. Okay, let's see. Okay, how does it look now?
Perfect.
Let me see if I can advance. Oops.
Yes, it's working.
Okay, cool.
Great. So it's my great pleasure to introduce Professor Maryam Fazel. She is the Murthy Family Professor of Electrical and Computer Engineering at the University of Washington, with joint appointments in computer science and engineering, mathematics, and statistics. She received her PhD from Stanford University and her bachelor's from Sharif University of Technology in Iran. And she's really done many fundamental contributions to controls and optimization, and received many awards for that, including Outstanding Teaching Award, as well as the UAI Conference Best Student Paper Award with her student. She's also one of the director of the Tripods Institute. In particular, she directs the NSF Tripod Institute at the University of Washington. And we're really delighted to have her. I think many of us grew knowing her great research and contributions, and how she was the person who introduced the nuclear norm that later led to really great advancements in matrix completion in the field. So we are really honored to have you, Maryam.
Thank you very much for the very nice introduction. That's really kind of you. So it's a pleasure to be here in a Tripods Winter School and Workshop organized by the great Tripods Institute at Johns Hopkins. And I'd like to talk about policy gradient descent for control, global optimality via convex parameterization. Let me start first by acknowledging my collaborator in this topic. So first, my student, Yue Sun, he's a PhD student at University of Washington, and he's done most of the second part of the talk on the convex parameterization and its connection to policy gradient methods. And Jingjing Wu is another student at University of Washington who's recently graduated in the aeronautics department. And our collaborators also Ron Ye at Duke University, Sham Kakade at, well, formerly UW, now he's at Harvard, just moved, and Mehran Mesbahi at UW Aeronautics Department. So I'm very, very happy to have had these great collaborators. From all of them, I've learned a lot, especially in an attempt to try and connect control theory with reinforcement learning and more machine learning approaches. And I acknowledge the funding. So the motivation for the talk is basically the use of methods that we can call direct policy update methods. So in a dynamical system and control problem, you would try to design a policy to achieve some goal, and then you update this policy iteratively through, for example, gradient descent on some kind of loss. We'll make this more concrete, but this kind of class of methods for continuous state control problems are actually quite popular in practice and have been recently used a lot for very successful applications. For example, things in robotics manipulation, like the OpenAI robotic hand, the AlphaGo by DeepMind. All these very interesting problems are built on using policy update methods, as well as we can also use them in the context of harder control problems, like decentralized control. So these methods are used in practice sort of empirically, but often lack guarantees in terms of, for example, optimality or convergence rates or statistical properties, even if you pick the method and apply it to very simple problems. So it's only been recently that these methods have been studied in the context of even simple classical control problems. So speaking of classical control, here's the basic paradigm in control theory, just as a review. The feedback paradigm, you have a dynamical system with a state x of t, that's state at time t, it's some vector in Rn. It could possibly be hidden. Sometimes there's state observation, sometimes there's partial state. The output is yt, that's the signal that's coming out of the system, and it's a measurement of the state that is made available to the feedback controller in the feedback block that we have. The output of the feedback controller is the ut, which is the input signal that's going into the system. So in the control language, we have the controller, this box that in the RL setting, you would call it a policy because it observes yt, which are the available measurements, and it sets the control input ut, which you can call action or input that would act on your system. A typical goal in control theory is to design controllers, for example, to stabilize a system, an unstable dynamical system, as well as also optimizing the performance of the system. For example, minimizing H2 norm or H infinity norm of the transfer function from a certain disturbance signal to a certain desired output signal, here from dt to wt. So this is just an overview of the control view. Now, what are the gradient descent on policy methods? What do they do? Or we call it policy gradient descent, however, not to be confused with policy gradients as used in RL. I will explain that later. So what do we mean by it? What methods are we talking about? We refer to any method that iterates on the policy, that is the map from state to action or input, that we denote by K here abstractly. That's the same as the control box in the picture before, the controller. So we use the words controller and policy interchangeably here. Using first order oracle, which means some computational oracle that can return the gradient of some cost function as a function of policy. So the type of methods we will be studying would at first be these kinds of methods that have access to a first order oracle, some information about how much does your loss change as a function of the policy, evaluated at the current policy. And then you update your current policy to K plus the next policy, which is just a gradient step on the current policy with some, let's say, step size eta. Okay, so why are such methods interesting? First of all, they are broadly employed. As I was saying, practical versions of this method have been used very successfully in practice without enough theory, but popular in practice. They're easy to use, very easy to, once you have an oracle that can give you the gradient updates are easy. There are many variations of these methods, for example, natural policy gradients, using natural gradients, or even methods that are more quasi-Newton-like, that weight the gradient with some matrix, and so on. And it's also not hard to incorporate additional constraints, for example. often convex constraints on the K. Well, not all constraints, but certain constraints are easy to incorporate. And also we have access to well-developed first order optimization theory that we can use. Further, if first order information like gradients are not available, one can go to derivative-free or zeroth order optimization. And zeroth order versions of these algorithms, their analysis follows from the first order analysis. It's related. So it's we can draw on the well-known first order and zeroth order optimization oracles in optimization theory. And if you use the zeroth order versions, that's actually very close to what people call model-free reinforcement learning methods or policy gradients. So the word policy gradients in RL usually refers to a zeroth order method. I'm using it here for this talk as a first order method, but results for derivative free can also be obtained, and I'll point out very briefly later. So what are key questions? First question is, when does gradient descent on K, on the policy, converge to the globally optimal policy? So this would be very desirable if one can prove it. Under what conditions would this happen? And if it does, what's the rate of convergence? And if gradients are not available, and if you have just samples of the loss as a function of policy, just function values, not gradients, what do we do? So that would be the zeroth order approach. And in particular, these are challenging when loss as a function of K is not convex. If it were convex, it would not be a big deal, well understood. But when it's not convex, a lot of questions are, it's much harder. So we'll see what to do. So just to put this study in some context, here is sort of a list of broader literature trying to connect control theory and learning, basically the learning and control. So it's not a very new topic. Indeed, it goes back to 90s. There is pioneering work by Bradkey on online adaptive control, by Future on actually packed learning results for adaptive control. And of course, remarkable book by Bertsekas and Tsitsiklis on neurodynamic programming, and further work that came after that. So there is a long, basically, history of connecting learning and control. And more recent work involves trying to study gradient descent, for example, on policy. One of the works that actually studies gradient descent is the highlighted one by Moritz Hart, Ben Recht, and others, which actually is not a control problem, just a system identification, trying to observe system dynamics and identify the system via gradient descent. And indeed, they impose conditions that makes that problem quasi-convex, and very nice convergence results are obtained. There is another line of work connecting control and learning, which is much more episodic. So first learn the system, first do system identification, and then do control. And sometimes you do that repeatedly in different episodes. There's also a line of work about more online learning and online control. And finally, the last reference here is a paper in control theory that used gradient descent to solve structured control design. So with structure constraints on the controller, which is not a convex problem and is hard. However, gradient descent in that setting worked quite well. There is no theoretical guarantee in this paper, but empirical evidence is there that it's working well. So in summary, there is a long line of work with varied emphasis on what is learned, whether a model is learned before control is designed or an approximate model is learned, or you try to avoid learning a model and try to learn an optimal policy without explicit system identification. So we are more interested in the second setting without trying to do explicit system ID. So this talk, first we will revisit the LQR problem, Linear Quadratic Regulator, which arguably is the most basic control design problem in control theory. In this problem, the loss as a function of policy is not convex, but we had a paper joint work with Sham Kakade and Mehran Mesbahi and Ron Ye in 2018, where we showed gradient descent actually does converge to the globally optimal policy. And the particular property that helped us show this is the gradient dominance property of this function L of K. And then I'll talk a little bit about, there is a long line of follow-up literature and very interesting results that adapted this kind of analysis to other control design problems, including robust control descent, certain type of decentralized control, linear quadratic games, and Markov jump systems, which can also be optimal policies under the right assumptions can be obtained by gradient descent on policy. And finally, the important message of the talk is actually we present a simple and unified view to all these problems. Basically, why does gradient descent really work on these problems? Via convexification, or use of classical control parameterizations from control theory. First, we'll do that for LQR and then more generally. So let's start with LQR, Linear Quadratic Regulator. This problem has a long history, goes back to Kalman in the 60s. And here's a picture of Rudy Kalman receiving the National Medal of Science, I believe in 2008, and the White House. So he did seminal work on many topics, including the LQR problem. LQR problem in continuous time is written here. It's x dot of t equals axt plus but is the system dynamics, xt is the system state, x0 is the initial state, and ut is the control input. The objective of LQR is we want to minimize, we want to use a low cost input ut, where the cost is defined via a quadratic function. There are several versions of this problem. Here we are looking at a specific one where you have a quadratic penalty on the state, x transpose qx, a quadratic penalty on the input, u transpose ru, summed over time. But we allow the initial state of the system to be random, chosen, for example, from Gaussian distribution with a covariance omega, or any distribution, basically. But we are interested in the expected value of the LQR cost under random initial state. And there are multiple ways to interpret this. It's a way to make the cost be independent of initial state. Okay, so for this cost, the goal that this is capturing is we want to steer the state of the system towards 0, that's the desired state, while keeping the input energy or the norm with the matrix R, penalized with matrix R, small enough. So the solution, as I mentioned, has been actually studied since 60s, and there's beautiful closed form solution to this problem. The stabilizing policy that minimizes the cost is actually given by state feedback. So UT is a matrix, a fixed matrix K star times XT. So static state feedback. And this matrix K star has a closed form formula. It's given by this minus R inverse B times P, where R and B are from the problem description, and P is the solution to this equation down below, which is called the Riccati equation. There are many ways to try and solve this equation using methods based on linear algebra, iterative methods, etc. And once a P is found, one can plug it in the equation right above and get the optimal controller K star. So this is the traditional way to solve the LQR problem, typically assuming you already know the dynamics A and the matrix B well enough, and Q and R. So all the system parameters are already known. You can solve and find the optimal controller. Now, what about applying policy update methods in this setting? So this was first studied in our paper in 2018 for discrete time LQR problem. So I just showed a continuous time version of the problem, but we'll go back and forth between discrete and continuous. Our 2018 paper focused on the discrete time LQR. And first of all, it showed that the cost, the LQR cost as a function of control policy K is not convex. And it's also not quasi-convex. It's also not star convex. As soon as the state dimension is bigger than or equal to 3. For dimension 1 and 2, actually, it is convex. So this is not that hard to show, actually. You can create counterexamples. For example, take specific two stabilizing controllers, and you can then show that if you pick them well, you can create a convex combination of the two that is not stabilizing, that the cost, LQR cost blows up to infinity in that middle controller. So this clearly shows that the problem isn't convex. and the loss is not convex as a function of K. Remember that the loss is also implicitly capturing that K should be a stabilizing controller, so that your value of Lk is not infinity, that is bounded. Yeah, so a little more detail on that. This problem also has the property that Lk goes to infinity as K approaches the boundary of the set of stabilizing controller. And this is a coercivity of the loss as a function of policy. And we also showed that L as a function of K, loss as function of policy, has this very nice property that is gradient dominated, which means the norm of the gradient squared at every control policy K is bigger than or equal to with some constant. So the tilde shows hidden constants. Bigger than or equal to the distance of the loss value to the optimal loss. So Lk minus Lk star. And here K star is the globally optimum K star, is the best policy. So this is a really strong property. It essentially says as the norm of the gradient decreases, you are approaching the global optimum. So if one shows this property, then the rest is not too hard to show. Now gradient descent works or other versions of gradient descent work. Essentially, it's the property of this loss that makes it very nice. The loss landscape, even though non-convex, is nice. So, so we showed this property, and then follows that the gradient descent on K converges to K star from any initial K0 that is a stabilizing controller. So we do need the initial K0 to be stabilizing. And then from a stabilizing K0, you get a linear rate of convergence to K star.
Maryam?
Yes, question?
Very naive, very simple question. Can you clarify what exactly you use for the cost and how are you handling the constraints? And the reason for my question is that your first statement is that it's not convex, but the counterexample is more about the constraint set. So are you incorporating the constraints into the objective, or what do you mean?
Yeah, very good question. Indeed, to write down L as a function of K, you do have to bring the constraints and incorporate it in the cost. So the cost L of K really captures the constraint, which is K is a stabilizing controller. It also captures that. For the LQR problem, it's actually quite nice. I didn't write it down, but one can actually write down L of K explicitly. It's the solution of the Riccati plugged back in. And then, yeah, that U equals Kx with this K star solution plugged in is plugged into the cost. So it's a complicated function of K, but it can be written down, and that function is not convex. It implicitly incorporates that K is also stabilizing controller.
Great. And then can you repeat, yeah, exactly, the gradient dominated and how that is used to derive the rate?
Yeah, so the details I won't cover here, but it's actually quite easy after you show that the function is gradient dominated, because essentially it's showing you that as your norm of gradient becomes small, it's just pushing Lk towards Lk star. And the rate really just depends on the constant over there. So yeah, so this property essentially is really showing the convergence. There are more general versions of this that are called PL inequality, where you can have some power alpha on Lk minus Lk star, and then that alpha would determine the rate. This specific one, which has power 2 on the left side and power 1 on the right side, is called gradient dominance and results in linear rate.
Great, thanks.
I have another quick question.
Yes, please.
Can we also establish this gradient dominance or PL condition, for example, for the Gaussian setting LQG problems where we have Gaussian noise to the linear system? Is it known, or?
I think noise isn't a problem, but LQG, the problem with LQG is partial state observation. Yes. Output feedback. So output feedback is much harder. So we are actually currently working on it, but there is also some work studying the LQG problem, which so far showed mostly negative results. That basically the landscape of LQG is hard, it has saddle points, etc. So, so some more approaches would be needed. This thing that I'm talking here won't directly apply to LQG. So thanks for the question. That's a good question. So then just as an aside, I'll point out, so we'll be mostly talking about gradient descent and having access to gradient of the loss. But a practitioner would say, oh, I often don't have access to gradient of the loss. And in those scenarios, as I was mentioning earlier, we can use basically zeroth order methods, which take the values of the loss that are measured, just the function values, and estimate the gradient from those function values. So you get a noisy estimate of the gradient, and then you simply do gradient descent with that noisy estimate. And many versions of these algorithms have been studied. One that we did characterize in the 2018 paper that I mentioned is that it's the simplest version of the zeroth order methods. So you add noise to actions during rollouts. Rollout means like a finite horizon timeline where you apply your controller and you see how the state evolves for a limited time. You can view it also as an exploration sort of phase, but usually very short trajectories. And so you do this and you collect the observed states, and then you use that to estimate, and you measure how much the loss is, and you use that to estimate gradients and essentially update. And this is the simplest version. There is many more fancier methods in zeroth order optimization that can be used as well. For example, other derivative-free methods, for example, 2-point estimates, multi-point estimates. And actually there are papers which extended those methods to explicitly to LQR problem and did it via these better estimates. We were simply taking one-point estimate.
Another question, Maryam.
Yeah.
The results assume knowledge of the system dynamics A and B. If those are learned, and say one were to have a bound on the error between the true A and the learned A, how do the results change?
So that would be more along the line of some of the papers I mentioned in the literature in the beginning, which do system ID then control, or a coarse system ID then control. Here, the goal is to try to not do that. So you don't know A and B. The motivation is that you don't know A and B, and you only have oracle access to either gradient or just loss value, function value. And the model that is closer to the reality of what people do in robotics and RL is the zeroth order one, is that you do not have full gradient access, but you do have these methods of measuring the cost value. So for those settings, it's helpful to just do this policy update without actually identifying a model. I mean, it's one choice. One other choice would be, let's just observe the system, identify a model, and so do this system ID then control approach. Yeah, so both are possible. But here we are showing that it's possible for it to work even without learning A and B.
Yeah, it was not very clear to me maybe how one computes the gradient of the loss.
Yeah, that's a good question.
Without knowing A and B.
Yeah. For gradients, I believe it's maybe more of a theoretical construct, but for zeroth order method, it's actually pretty doable. Because zeroth order says you just have to, oh, sorry about noise. You just have to measure the loss given a policy. So you are at a current policy, you perturb the policy and just see how your loss is changing. And you measure it in a few points, only a few points.
Yeah.
So that's the more practical. Access to a gradient oracle, as you're pointing out, may be viewed as impractical if you don't know A and B. That's true. But it's actually our first step, really. We first analyze gradient oracle, and then a zeroth order oracle can follow. In some cases, I believe in controls, people do assume you have gradient oracles, but I'm not completely sure what the settings are. Yeah, that's a good point. Yeah, these zero order methods also extend to variations on policy, gradient policy, gradient descent on policy, for example, natural policy gradient methods. Yeah, which I won't get into details, but some variations also work. So there has been a lot of recent research interest in following this line of thought that if you do have gradient oracle, and if you update your policy according to that, do you converge to K-star? And interestingly, there is a whole set of papers that came out that showed this was true for a bunch of different control problems. So our work did the discrete time LQR. There was also work on continuous time LQR, several papers on that by a group of Mihailo Jovanovic and also Mehran Mesbahi. The also robust control and H-infinity control work from the group of Tamer Bashar. There is work on structured finite horizon LQR. Now, finite horizon is a little different and it's in some sense easier without the stability concern, but still can also be shown. This is work by Maryam Kamgarpour and co-authors. As well as they also showed this approach works for decentralized control under quadratic invariance. So this particular version of decentralized control is actually known to have a convex formulation as equivalent to convex. There's also work on linear quadratic game setting, very interesting. And there's also Markov jump linear systems version of the problem. So you actually have time varying system where there's Markov jump between the different systems, and that has been also shown. And I'll revisit some of these examples towards the end of the talk. So the approach in these papers was that each solves a specific control problem, each are focused on their specific chosen problems, and they follow basically the same style of proof that I was mentioning, that you show your cost is gradient dominant by directly like brute force working on that specific loss function. So you can say these are handcrafted proofs, and they don't really give you enough intuition either about why these non-convex problems happen to not be too hard. But so here's what we are going to discuss in the rest of the talk. If a control design problem can be convexified, if it does have a convex parameterization in a different space with different variables, not with our policy variables K, but if it does have a convex form in some other space, does policy gradient descent converge to global optimum? And the answer to this will be yes, and that's very interesting, I think, because it shows this property that's shared between all these problems is that they indeed have a parameterization that's convex in some other space. Let's see what happens if we have such a parameterization. To distill the properties that we would need, let's revisit the LQR problem. This is a LQR problem written in a convex form. This is a problem on the left-hand side. If there's time, I will explain where it came from, but basically this map A is just a Lyapunov map, AG plus GA transpose. B is a similar Lyapunov map. Sigma is the initial state covariance matrix. So this is the Lyapunov equation. And G is an auxiliary variable that's positive definite. And essentially, we called it P before. This is the same as our P, that's the Lyapunov solution. And this linear matrix inequality here links the G variable to the L variable and an auxiliary variable Z here. So this problem, if we look at it, we will see it is a convex problem. The cost is linear in our variables G and Z, and the constraints are all linear matrix inequalities in L, G, and Z. So it's a convex problem over Z and L and G, these variables. So that's the first thing we need. We need the parameterization exists that is convex. So constraint sets and costs are convex. And the next property we need is that essentially there exists a nice mapping between the two problems. So the non-convex form of the problem, which was this on the left-hand side, minimizing loss as a function of K for K being a stabilizing controller, which is not in general convex. For example, in LQR, it was not convex. That was the function we first talked about. We needed to have a nice mapping to this convex problem. And in the case of LQR, it's actually, it's a simple mapping. It's already studied. And that is that if you solve the convex problem and the G that you obtain is invertible, then the K that solves the first problem can be found by just forming LG inverse. So this means that we basically have a bijection between the set of Ks, the non-convex set of Ks, and the convex set of L and G and auxiliary variable Z. The role of the auxiliary variable is that there exists a Z such that LGZ is in a convex set. So as long as there is this is the first assumption that, that there's a bijection. Later we will see we don't actually fully need a bijection, but if you do have a bijection, that's great. The bijection needs to also satisfy that the value of the cost of the convex problem is equal to the value of the non-convex problem. So this just follows from problems being equivalent. So those two assumptions were a little bit special, and we assumed a bijection. Here's a more general version of the assumption, and this covers more problems than LQR. You can have a set of additional variables, let's say P1 through PM, and as long as we can express the control loss as a function of policy as a convex optimization problem over these P variables, and as long as there exists a mapping from the P space back to the K space, and this map phi bar is Lipschitz, so simply has a Lipschitz constant, then we have a result that links the that basically makes a statement about the non-convex problem of minimizing LK over stabilizing K. So under assumption, so the theorem says the following. It tries to say basically that whenever there exists this convex parameterization given on the right-hand side, that you have nice properties for L as a function of K, this non-convex function. So specifically the theorem, this is a slightly simplified version, is that under assumptions 1 and 2, 2 required the bisection, or 1 and 3, 3 was the more general one, as long as any set of convex parameters exist that capture the problem. Then any stationary point, any point where the gradient of loss with respect to K is 0 is optimal. So basically that answers the question about solving this by gradient descent. It would be then trivial that gradient descent would work. So more specifically, we can show, in order to also get quantitative understanding of how gradient descent would converge, for a linear or more generally a convex F, that is the cost in the convexification, in the convex formulation, we have this result. We have that it's like gradient dominance, but not with the right power. Gradient dominance is the one below. So if F is mu strongly convex, you have exactly gradient dominance with this power 1/2 here, which gives you linear rate of convergence. If you're not strongly convex, your rate of convergence from the result 1 is a bit worse, but still you get a rate of convergence. Now these C1 and C2 are constants that depend on the problem. For example, for the continuous time LQR, we can actually calculate it explicitly, and I will show it on the next slide. We start with a K0 that's already stabilizing. So you can look at the sublevel set of Ks where the loss is less than some value A. And then C1 and C2 will depend on that value A, which is not unnatural because it's the rate of convergence always depends on the distance to of the initial condition to the optimum. The sketch of proof, actually the proof is fairly simple. What we need to do is that when you look at the convex formulation here, come up with the inequality that bounds the norm of the gradient of this F function. This P of S here means you can think of it as a projection or restricted to the descent cone of the set S. So norm of the gradient as a function of L and G and Z, so this is the nice convex function, is lower bounded by the value of F minus F star. And this capital F here is some function. For example, it can be either linear, it can be square root, as we saw as 2 examples, but it can be more general other functions as well, like other powers, for instance. So we can show this easily because we are in a convex space. S is convex set, F is a convex function, so that's not too hard. But then we want to map this back to the non-convex space. So as this picture down here shows, essentially the idea is if you are at a point L and, sorry, there's a typo here, this should be, the P should be G, LGZ variable, if you are at a point in the convex set and you take the gradient of the convex function and you also find the direction towards the optimal L star, P star, Z star, all of those can be mapped back to the non-convex space, which corresponds to the control policy KT and the loss as a function of KT. So with this mapping back, which really only requires that phi bar mapping be Lipschitz, we can get a similar inequality of gradient dominance like inequality for the L of K. The function phi here could in general be a bit different from this F. And depending on what phi you're getting, again, the rate of convergence would differ, whether it's linear or square root and so on. So I'm skipping the details, but this is basically the general idea. Let's see what happens in the case of the LQR problem. So this is the convex form of the LQR problem with variables LG and Z that we saw earlier. And it's already known for LQR that the optimal controller is LP inverse. So the main question we need to check and make sure is our P invertible? Because we need to have a Lipschitz map and requires P being invertible. And actually, the answer to that is that yes, P will always be invertible if the initial condition we had a full rank covariance. This is interesting because the sigma matrix here is the covariance of the initial state. And this Lyapunov equation, the first constraint in the optimization problem, will always have a solution. Oh, I'm again mixing P and G. Sorry, G is the same as P. So the G here will be invertible when sigma is full rank. So that is known. So with our setup, the answer is yes, P will always be invertible. And how about their sizes? You would imagine P inverse would get very large. But if you're already in a sub-level set, there are bounds that you can have based on the problem on L, norm of L, P, and P inverse in the sub-level set. And so sub-level set is a sub-level set of the cost, which also had this form in the convex parameterization in terms of L and G, which is the same as P. So these would actually make it much more quantitative and give you explicit rates, like the constants in the gradient dominance. Well, this one is not technically gradient dominance, the PL condition. The constant can be given explicitly and it's written here. So you have dependence on sigma maximum singular value of the A matrix. There's dependence on the Q, which is the matrix in the cost, dependence on the B. And these are not surprising quantities. You would expect that actually all of these will show up. Dependence on R, as well as dependence on the minimum eigenvalue of the initial state covariance matrix, which is important, which we assumed was full rank. So this is not going to be 0. And so C1, which is exactly the constant that shows up, can actually be worked out to be this. And A is the value of the loss function at the sub-level set. So it's L of K0, basically. So we are assuming that we have access to an initial controller that is stabilizing, but could be very far from optimal controller. Now, there's other recent work as well about if you don't know the A and B, if you're in the model-free setting, how do you even come up with K0? You have to do like some kind of a phase 1 thing and first find K0 and then run the thing that the gradient descent that I'm talking about. But there is interesting recent work on how to do that, multi-trajectory, single trajectory, etc. So it's possible to, it's not too hard to find a K0 that's stabilizing. Okay. Right, so this LQR example, this is a discrete time LQR. Discrete time LQR is a little bit more tricky. The cost of LQR in discrete time will be an infinite sum like this. Still is known that the optimal controller is given by state feedback, Kx. And there does exist a convex formulation for this problem as well, a little bit different, but similarly, you have a convex cost. The cost is linear in your variables P and Z, and these constraints are all LMIs in P and Z, L, P, and Z. So this implies we can just apply our theorem and conclude that LK is gradient dominant. In this case, it is indeed gradient dominance with the power 1/2. A little bit more details about this problem. If you look at the Lyapunov equation, the sigma in the Lyapunov equation So the Lyapunov equation looks different and is actually trickier in the discrete time case because you have A plus BK on one side, P, then A plus BK transpose. So it's not actually convex in P, whereas the continuous time was convex in P. So you might think we need one more step to actually get a convex problem, and that's actually true. So continuous time case was easier. In the discrete time case, because of this quadratic form in K, we need to do a little more work. But in fact, it's one thing that is similar to discrete time, to continuous time, is that P is still a Gramian of the state, which is given by this equation. And your cost function has this form, which actually still does have convex form in L and P and Z, which is this form. Now, the only thing is that you want to impose this equality, and the equality is not convex. But we argue we can relax it to an inequality, which is then equivalent to an LMI. But however, this is not this is a lossless relaxation because the solution is always at the boundary. So these are well-known facts from controls. But it's helpful for us because all of this gives us this convex formulation for the problem. And again, applying our general results will show that so the mapping you work with is again the same as before, like LP inverse. And that's a smooth map, and you can find its Lipschitz constant and therefore find the constants in this problem. So LK would be gradient dominated, again, with appropriate constants. So these are the simpler problems, but let's jump to a much more complicated one. So a paper in 2020 looked at the Markov jump linear system, which is much more complicated problem. So you have the discrete time dynamics given by a linear system, but the system matrices A and B depend on time, and in particular depend on this variable W of t, which takes values from 1 to n randomly according to a certain probability transition function, which is written here. So essentially your system follows linear dynamics, but jumps to a new linear dynamical system according to this transition probability. So overall, much more complicated system. But it interestingly and nicely has a convex formulation as well. You can define a big K, which stacks all of the Ks corresponding to each of these n systems. And the loss will be a summation of losses over all of these. Summation over time and expectation over initial state and expectation over the W, the random jump variable. The optimal controller is also known in this case to be state feedback, but the feedback gain will change. So that's why we have a set of K1 through Kn optimal controllers. But it's also known that, again, there exists a convex formulation. It's in terms of the initial distribution of the W's and so on. So I won't go into the details of this, but it exists, and it's actually, you can see the constraints are all LMIs. So convex formulation. So from this, we can again conclude that the loss in this problem as a function of all of the Ks, here K means all Ks, K1 through Kn, is gradient dominant, and again can be, results for gradient descent can be shown. Another problem is dissipativity. So suppose you want to maximize the dissipation of a linear dynamical system. Dissipation is defined as this parameter eta, such that this quantity is bigger than 0 for all t. And this is the dissipativity inequality. And without going into details, I'll just say that in this problem, also the optimal K is going to be state feedback, and it does have a nice convex formulation. And interestingly, the map back from the convex variables L and G to the K is again LG inverse. So now you might say, well, is something very special about this map, LG inverse or LP inverse? So no, not indeed. We as we mentioned, there is, as long as you have a phi bar map that is Lipschitz, you're good. It doesn't need to have this particular form. Many control problems happen to have this form, but it doesn't need to. And in our paper, we have a few more complicated examples using, for example, system level synthesis parameterization, which is more complicated and the map is not as easy and simple. So, okay, let me conclude and then talk a little bit about some future directions. So for a broad family of control design problems that can be convexified, that do have a convex parameterization, policy gradient descent, meaning gradient descent on the policy variable with access to a gradient oracle. But we also said if you don't have gradient oracle, you can do zeroth order. So it's relevant to the zeroth order setting too. So policy gradient descent converges to the global optimum despite the problem being non-convex, because it's a very special form of non-convex now that we can see. All these problems have this nice mapping to a convex space. And rates of convergence can also be obtained. And in addition to Markov systems and the few examples that we saw, H-infinity problems, robust control problems, LQ games, and several other problems can also be analyzed, and system level synthesis type problems, finite horizon, time varying. There's multiple examples that actually do fit this model. A general concise proof method. So this gives a general concise proof method that connects the non-convex landscape with a convex landscape. And then concludes that gradient dominance type properties follow from this convex landscape and the properties of the mapping between these convex and non-convex sets. We can extend the results that we talked about from gradient methods to other related methods as well, like natural policy gradients. And Gauss-Newton variants and so on, the quasi-Newton type variants. And this also helps, as we just briefly pointed out, helps us design and analyze derivative-free versions, which are closer to what people in RL call policy gradients. Indeed, it is indeed exactly a zeroth order method. So which requires only a zeroth order oracle, which means just loss function values, no gradients. So you can do it in a model-free setting as well. So open questions, and actually Mahyar already asked this. LQG, linear quadratic Gaussian control problem, which is an output feedback problem, is indeed much harder. So this is our future work. And the optimal controller in an LQG problem is a dynamic controller. So it will not be a static K, but will be itself a dynamical system. So your variables will now be the system variables of this controller block. So far, what is known about this problem is mostly negative results about how kind of the landscape is nasty, the set is nasty, etc. But there is hope that with the right assumptions, we can still possibly do something here. Next future direction would be, can we get better convergence rates on specific problems from this general analysis? So the general analysis doesn't point you to how to get the best constant C1 and C2, and your rate would depend on those. So you may want to figure out how to specialize it to each problem and get the best rates. And control theoretic interpretation of these constants would be interesting. Some of them are kind of big and nasty, and while it has a lot of sigma min and sigma max of the matrices involved and so on, it will be nice to try and connect them to things like radius of stability or more interpretable quantities in controls. So with that, I'll just point out that we have a short version of the second part. So the first part of the talk was our 2018 paper in ICML. We didn't list that one here. The second part of the talk, there's a short version that appeared in CDC of 2021. We will post a cleaned up long version on archive soon. If you wanted to see our current draft, it is online, but not yet on archive. Once it's in archive, it will be a bit nicer and cleaner. So with that, let me stop, and I'm happy to take any questions.
Thank you, Maryam, for really a fantastic talk. Again, if you have any questions, go ahead, or otherwise type them in the Q&A.
Hi, Maryam. If I
go ahead, Enrique.
Hi, how are you? Yeah, I guess like my question is, just wanted to verify that this general principle that you were talking about, is this like a fact of optimization, meaning that like for any non-convex problems where there exists like a map that like transforms the problem into a convex one, then provided that there are certain conditions on this map, then gradient descent is going to work?
Yeah, this is essentially very general. That's right. It's really about, yeah, exactly, mapping the spaces and the conditions on the map. But it's for these control settings, it's quite interesting because you can write down that map, and in many cases, it's just this LP inverse, which is very meaningful, and its properties are well understood and well studied already. So it's very helpful. With this observation, all these control problems, instead of one-by-one proof, you can just conclude results about all of them at once. But yeah, the result is more general indeed. This doesn't need to even be a control problem. I mean, in very high generality, maybe it becomes a little vacuous though. It just, yeah, I mean, so it depends on that map. You need to characterize the map that links the non-convex to the convex problem. And a lot of details of that map need to be known, and its Lipschitz constants and so on.
So you're saying Lipschitz is probably the key property that you need in that map?
That's right, that's right. Now, I think if you add more properties, you can get stronger results. Okay. But this basic one, yeah, just Lipschitz.
Okay. Thanks.
Yeah, thanks.
I have two follow-up questions. I had almost the same question, but more specifically, one can have a convex parameterization, and in this case, it was through this set of variables P, and there were M of them. But presumably, one could construct another different parameterization, maybe with M plus one variables. Like once you have with M, you can even over-parameterize. So I was curious as to the fact of how flexible this is, because presumably there could be many parameterizations, it may not be unique. And how is it the case that no matter how you do it, you're going to get the same result and the same convergence rates was very surprising to me.
Well, so one place, actually, that's a very good question. I don't have a very good answer. I've started to think about it. But one place where the specific convex parameterizations properties show up is, and in particular, if you have more P's, you're going to hurt your, like, it's ideal to actually find the minimal convex representation. If you actually add spurious variables, you're going to hurt your constants that appear.
Yes. But how do the theorems and the equivalence prevent those over-parameterizations from showing up? That's what I was trying to understand.
Yeah, ours, we're not preventing. You're basically saying that, so, you know, the constants here really do depend on what formulation you use over here. And you can get really bad and almost vacuous results. If your, for example, your convex parameterization was infinite dimensional, you're not going to get anything.
Okay.
So then you can, but it doesn't really give you anything. You see what I mean? So there is a mapping, but so yeah, it's good to quantify that. It's a very good question that what about the sizes of variables and the dimension of the convex problem precisely show up in these constants and how? But certainly those things do show up, and it's kind of clear that you want a minimal convex representation over here to get the best result.
There are two questions online. The first one is very related. I read it. The condition has a convex representation in some space seems rather weak. I seem to recall the work by Lasserre showing that most problems have a convex representation in some space, possibly high dimension. Does the complexity of the representation here have a practical consequence with respect to convergence guarantees? I think you've partially answered that already.
Yeah, I think the answer is yes, and I think it will show up in the constants to the point that these might completely ruin the convergence. Well, certainly infinite dimensional will not help you at all, because yeah, all non-convex, pretty much polynomial non-convex problems can be written in a dual form in the measure space, and they're convex in the measure space, but they're infinite dimensional. So that's not going to help. Yeah. But how precisely the dimension of the convex formulation affects things, we haven't yet worked out. That's a really good question.
The next question is there a general method or procedure to make any control problem convex? Is it ready to use in real devices and robots?
No, many control problems are just do not have a convex formulation. So these are, it's kind of nice because I don't know if I mentioned, but yeah, I guess I didn't mention. So there is a long history of work in the control theory about convex parameterizations, going back to the Euler parameterization, which I wanted to mention, I forgot to mention it here. Euler parameterization back in the 70s already gives you this control, stabilizing controllers all parameterized in a convex way for LTI systems. And then results that build on Euler, there's interesting work on, very nice work called Q parameterization. Actually, that is, there's a book by Boyd and Barrett, 1991, that uses Q parameterization to design, to do control design. It's also a convex formulation for a many set of control problems. There's also all other known LMI representations for different control problems. Like you can look at a book of Boyd et al. LMI book from 1994, as well as I think a more recent textbook by Karsten Scherer. So all these control researchers have identified many families of control problems with a convex parameterization. But certainly many problems also do not have such a parameterization and are known to just be really NP-hard.
Great. Well, thank you very much, Maryam, for such a fantastic talk.
Thank you very much for having me and for great questions.
Mayar, I think you're next.
Yes. So I will
try.
Yeah, I will sign in my iPad so that I can also.
Is Rama Chelapa on the audience?
So can you see my screen?
Let me, yes, we can see your screen. Do you want to try moving forward and backwards? Yeah, okay, great. So it's my great pleasure to introduce Professor Mayar Fazel. He did his PhD and postdoc originally at the University of Pennsylvania in the Department of Electrical and Systems Engineering. He's been doing a lot of work in the general area of systems and controls, as well as learning. In particular, has done work in the robustness of deep networks, as well as guaranteeing Lipschitz constant for deep networks. And he's also been recently working in various areas of optimization. Starting this past fall, he moved to Johns Hopkins, where he's currently an assistant professor in the Department of Electrical and Computer Engineering, and also a professor in Mainz. We're really delighted to have him, and we look forward to his talk.
Thank you, René, for the kind introduction. Hello, everyone. So it's my great pleasure to speak in this fantastic event. So today I'm going to talk about some of the control theoretic and optimization-based tools that I have been recently developing for the analysis and synthesis of neural